welcome to lecture 6, and we are going to start off strong with Schrodinger's cat. Basically, they took a cat, and this was in the early 1900s, I believe, so this is before there was a whole hammer down on any sort of animal testing, animal abuse, but they did this experiment where they took a cat, they put it into a box, and had a radioactive substance in there, and if the radioactive emission is detected from this substance, the detector releases a hammer and poison gas is released. But there was no noise, there was no buzzers to actually help the scientists determine whether or not the poison gas was released or not. Basically, the philosophy was, at any point in time, is the cat alive or dead? They don't know until you open the box. So until you open the box, the cat is technically both alive and dead because you don't know. So this is a very kind of weird analogy in order to explain how electrons actually behave. Section 2.2 is about the nature of light. Since electrons behave similar to light, we can discuss kind of how it flows. So electrons can be oscillating, which means basically going up and down like this. They can be oscillating waves or they can be particles. And at any given point, they are both. And what we're going to learn here is that when you try to actually measure these electrons, they behave differently when you measure them. So we've measured them and they've been a wave, and we've measured them, or we can see that they've been a wave and we can see that they've been particles, but whenever we measure them, it changes, so we can't actually tell which is a wavelength and which is not, because our measurement tools actually use its own light, and which in turn affects the electrons, because whenever we say photons, we also mean electrons, because excited electrons are what gives us light. So here, electromagnetic radiation can be described as a wave composed of oscillating electric and magnetic fields working in perpendicular planes. So this plane is slicing through all of these more upright pieces, so this is the perpendicular plane, and this is where it's traveling through. Electromagnetic radiation is not super important. It's important for understanding, but it's not important in the fact that unless you go into a very niche field, you're not going to be using electromagnetic radiation or anything about it in studies or anything, or at least I haven't. But I'm, again, a biochemistry major, so you might go into a field that does electromagnetic radiation, and that's great. So here, we are going to talk about wavelengths. This is a big study, and it is very important to learn everything you can about wavelengths because it's going to come up quite often. I'm in my 4th year, and I'm still learning about wavelengths. I'm still using stuff about it. From the 0 point up to the highest peak, or even here from the lowest peak, or here to the highest peak, this is the amplitude. This is basically how high a wave is. So take note, amplitude is measured for only half the wave. So a wavelength is actually from here to its point here. So basically it going up from 0, across 0, and then back to 0. So when the wavelength, and this is lambda, this is the Greek symbol for lambda, and this is described as wavelength in generally most areas of study. Here we can see different wavelengths are different colors. The slower wavelengths get more into the red region, and here we get more into the yellow region as the wavelengths are starting to like speed up and be faster. And then here we're getting more into blue light and the wavelengths even faster. This is frequency. So this is a higher frequency and this is a lower frequency here. So when the wavelength changes here, so does the frequency. Frequency is this really curly QV. In fact, wavelength and frequency are inversely proportional to each other. Longer wavelength equals shorter frequency. So when they mean longer wavelengths, they mean there's more space here, so in the wavelength. So you can see here, this wavelength is much shorter and this wavelength is much longer. So the longer the wavelength, the more it's stretched out, and so the lower the frequency. Here we can see that different amplitudes are different brightnesses. So these three here would have the same amplitude and they would all be the same brightness level. But here, it's much closer to 0. It's dimmer. And here, The electrons are like way more scattered. They're more excited. They're not in their natural little zero state here along this line. They're a lot brighter. They're giving off more excited energy. So amplitude is independent of wavelength and frequency. It has nothing to do here. It's not, the amplitude's not going to change the wavelength, and the amplitude's not going to change the frequency. It's just basically its own thing. This equation describes the relationship between wavelength and frequency. So we have our frequency, our little curly QV here, which equals c, which is the speed of light. This is the speed of light right here. It's 3.00 times 10 to the 8th, or E8 meters per second, or you can also read it meters second to the -1. This right here, -1 to this s, basically means divided by whatever the value is here. M over s is the same as m times s to the -1. If m was to the -1 and it was times s, then it would be s over m, if that makes sense. And then we have wavelength divided here. So we can see a high frequency here, where it's really fast, and we see a low frequency here. And you can see low frequency is closer to red, and high frequency is closer to blue. So this is an example problem here, which I really urge you guys to do, and I urge you guys to even put in your own different values as well. Keep in mind that c is always going to be 3 times 10 to the 8. It is a constant, which means it is going to be constantly this number. So whenever somebody says constant, they mean it is going to be a specific number every single time. Not all constants have values like this. You guys will learn that later. But most constants will be given to you, or you'd have to memorize them like this. But typically they are found out through rigorous scientific studies, so that way we can use them to discover other things. So rearranging this equation here, we get wavelength equals c over v. This is very important. You guys got to memorize this. And inputting the values that we have here, so 4.62 times 10 to the 14th second to the -1, we get, because these second -1s cancel out because they're above each other, we get the wavelength is 6.49 e -7 meters, or converting it to nanometers, remembering your conversions, we get 6.49 nanometers. Wavelength is usually always going to be in nanometers. That is the units for wavelength usually. I believe red wavelengths are around in the 500s, I think. So yeah, we can, oh, okay, sort of, about 500. As we can see here, this is a spectrum, the electromagnetic spectrum. So this is all the light we have. So this is all the visible light. And the visible light is this rainbow we have here. So us humans, we can see this entire spectrum. We can see all the reds over here going down into orange, yellow, greens, blues, and purples and violets. This is our visible range. And then we get into the things that we can't see, like infrared, which is a lot more longer wavelength than visible light, and we can't actually start to see it anymore. Then we get into microwaves, and then radios. We can't see radio waves, we can't see microwave waves, and we can't see infrared waves, but we can see these. And then it gets to ultraviolet, so UV, that's kind of like the sun, the rays of the sun. Then we get into x-rays, like going to the doctor and getting an x-ray scan so they can see the waves like penetrate through your skin, and they can see your bone and the density differences. And then there's gamma rays, which you do not want to mess with. We can see here that infrared is a little bit longer than visible light, and UV, or ultraviolet, is a little bit shorter than visible light. You can memorize what ultraviolet and infrared is, because if you know red is high in like the 700s, and infrared, you know red is further than 750. And ultraviolet, violet is 400s, it's even further than that. So that is how you can kind of remember a little bit how that works. So here we have interference and diffraction, which is actually pretty important. So if you guys ever looked outside and you see puddles and there's raindrops or something dripping in there, or you threw a rock in there, or a bunch of gravel. So if you threw a bunch of gravel onto a puddle, every single piece of gravel will form its own ripple, right? And once all the ripples are going to bump into each other with all that gravel thrown in. If you observe it, you can see that all the ripples kind of cancel each other out. The surface kind of goes pretty smooth. the edges of the puddle aren't really going to move back and forth like an ocean wave coming onto shore. But if there's one big rock, then it's going to radiate out, and just like the ocean, it is going to cause a wave around the edges of the puzzle, and it can get actually pretty big. Here we can see that it's the same with electrons. When the waves are in phase, which means basically they're going at the same time, you can see here they're matching each other, then this is constructive interference. Constructive meaning it is constructing a bigger wave. It is becoming a much bigger wave because they're in sync, so they become more powerful together. But when they're out of phase, look, these two are completely opposite from each other. They're canceling each other out at every single point. Therefore, we have destructive interference. So that surface of the water is going to be kind of still, and because all the ripples are going to cancel out. So here we can kind of see it. So when we are trying to measure electrons, we usually have some light and it goes through this slit. So the size of the slit is similar to the wavelength of light. And this can be pretty confusing at first, but yeah, you'll be able to kind of see it as we go. Wave diffraction is basically when these wave crests go through this slit and they become different waves that all kind of are constructive with each other. And this is how waves behave. So you can see that everything, it's kind of weird to see it here and it doesn't make quite sense when you see all these lines, but this is basically a beam of light coming in and then it's going through a slit. Then it turns into basically what we saw here, all these waves. And we can see that the light intensity at its highest point is going to be the brightest here. And then it is going to get smaller as it goes out, as in it is going to, it's kind of like the edges of the ripples as it goes out, it kind of gets smaller. So this is basically what's out. This is the center point of impact of that rock hitting the puddle, basically. This is that center point. This is the biggest point of the, or this is the most intense point that you're going to have for a diffracted wave. Diffracted just means bent. However, if you have a particle beam, so this is what particle behavior is. All these beams hit, and because there's a slit, only right here, like 2 beams are going to go through, and there's not going to be all these slowly fading out until we can't see it, pieces of light. There's going to be just one blip of light right here, and this is how particles behave. So waves are going to be way more spread out with an intense point where it's strongest, and then particles are going to hit one spot. And that's going to be it. Stay with me here. This is going to get kind of complicated. This is when you have interference. So if you have your light source here, and we have our waves going out, and then we have our 2 slits right here, we can see that when they come out, they are going to start interfering with each other because it was one big wave here, but now it's become its own little wave here. So we can see the waves out of phase, they make a dark spot, and the waves in phase make a bright spot. Because again, when it's out of phase, it is going to cancel each other out like ripples, and when they are in phase, they're going to be a lot bigger and stronger. And when they're stronger, that means the electrons are a lot more excited because there's way more electrons with them now, and all of them are working in unison. So they're super, super happy. They're going to let off a lot of light, and we're going to have all these white spots. So that's why having a light source with waves here, it is going to cause this image on the film where there's light spots and dark spots. So now we have the particle nature of light, and this is the photoelectric effect. So the fact that metals emit electrons when light shines upon them. So the photoelectric effect is basically when you shine a bunch of light and it hits this metal surface, and this metal surface is connected to this meter, which measures the current, or basically the amount of electrons that go through, the voltage, which is connecting up to this battery, which goes into this positive terminal. So when light hits this metal surface, the light is going to excite the metal, the electrons around these metal atoms enough to where it whoop, and it flies off. So when an electron is ejected or comes off of these metal atoms, it will hit the positive terminal and complete the circuit here. So the measured current goes up as the number of ejected electrons increases. So we can actually measure different types of metals and how easily electrons are removed from it through exciting them with light, because putting all these photons or other electrons on it will get all these other electrons excited, and then they'll they'll fly off. So in order for an electron to be emitted from the metal, the light particle must give the electron enough energy to escape the metal atom, and this actually varies from metal to metal. It is also known as the threshold frequency. Note that the frequency, not the amplitude of the light, is the determining factor. Right here, we're not looking about how close that wave is to zero. We're looking at the frequency, or how fast it is moving. So remember the frequency of light here, it's how close together these waves are. Here we can see the threshold frequency, the rate of electron ejection, it's not going to be ejected that much with lower light intensity. With a higher light intensity, way more photons, way more electrons hitting that metal, more photons per unit of time, more electrons are going to be emitted, or basically flown off of the metal atoms. Why is frequency specifically, though, used for the determining factor? Well, back in the day, Einstein proposed an explanation for the photoelectric effect. Light energy must come in packets, basically. The energy in one of these packets is directly related to the frequency of the light. So here we have E, which is energy, equals H, which is Planck's constant. So Planck, in the 1900s, I believe, he came up with this number basically saying this is the amount of, or energy times seconds, in a given second, I believe. This is used in order to calculate how much energy a photon has given its frequency, or how fast it's moving. Since V equals the speed of light over the wavelength, you can actually rewrite this as the energy of a singular photon equals Planck's constant times the speed of light divided by the wavelength. So keep in mind that H and C are both constants, and we know them. So here, as long as we have the wavelength, we can actually calculate the energy of a photon. But keep in mind, you cannot have a fraction of a photon, which suggests that light behaves as particles of a specific size. So a nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? Here we are given our wavelength and we are given the amount of energy. So now we have to figure out the amount of photons it has. Just a little hint for you guys, because I want you guys to do this on your own. This is similar to a question: if a golf ball weighs 45 grams, how many golf balls do you have if you have 900 grams of golf balls? You have your wavelength here, calculate it into this, and if you have this much energy and you find this, that's basically saying you get your 45 grams and you get your 900 grams. So you are able to figure out how many photons it contains. I believe in you guys, you got this. So as stated earlier, a photon must have enough energy in order to eject an electron from an atom. This is not the same for each type of atom or for different electrons bound to a particular atom. This amount of energy required to remove an electron from an atom is referred to the binding energy. So basically, how much energy does it take to take an electron off of an atom, because that electron is bound to it. So this is related to the frequency of the photon. If the photon of light has more energy than needed to eject the electron, then the remaining energy is transferred to the electron in the form of kinetic energy. This binding energy, or the threshold frequency, so basically how much light it takes to knock off that electron, or the rate of electron ejection. So remember, lower light intensity, less electrons are going to be ejected. So if you have a higher light intensity, or the photon of light has more energy than needed to eject it, so it's more than the threshold frequency, then that electron is going to keep all that remaining energy, and it is going to transfer to the electron in the form of kinetic energy. So basically, the higher the light intensity, the faster that electron's leaving, because kinetic energy is how fast the electron's moving. So we actually have another cute little equation here, and it is Ke, so this is kinetic energy of, so when it has a subscript here, it's usually saying of something. So the kinetic energy of the ejected electron equals Planck's constant times the frequency minus the threshold frequency. Given all these, because remember, you got Planck's constant, so if you can find the frequency and you know the threshold frequency, you can actually calculate how fast that ejected electron is moving, which is pretty cool. So keep in mind, make sure to try this example, and if you get stuck, let me know. I will try my best to help you out. And good luck studying, make sure you drink water, and I will see you guys in the next lecture.